let's get started. I will begin with a word of prayer. Here we go. Dear Heavenly Father, we thank you for this day again. I thank you for this class, for these students. Just ask you just bless our work today. Help us to glorify you what we do. I just pray that students will be encouraged just to continue to try to do their best each day, Lord, for your glory. And I just pray that they would be able to understand whatever it is that they've missed in this course up to this point, and that they would just make good use of the time that remains so that everyone could have a successful experience this semester, Lord. In my prayer, Lord Jesus. Amen. Amen. All right, so here's some properties of, I don't know why there's so many chairs up here. It's hardly any room. So I've written on the board the properties of the exponential function, all right? So the exponential function, so here I'm assuming a is greater than 0, okay? And I usually think of a as being greater than 1, but a could be a half. It'd still be okay, all right? I guess a could even be equal to 1. It would just be kind of silly. And people do look at log of like base a half. It's true. But I just don't feel the need to discuss that in here, except to say that it's something you can do, but I've never really had a need to work on it. So I'm going to focus all of our energy on the case that the logarithm has a base larger than 1. So like log base 2 or log base 3 or whatever. So these are the properties of the exponential, right? And we've used these before in the course, right? All right, so there's that. Now, and the logarithm is the inverse function to the exponential, which means it has these two relations right here, right? But what's possibly new for you are these properties right here, right? These might be new. So these are the properties of the logarithm. The sum of the logs is the log of the product. A difference of logs is the log of the quotient. And this last one I refer to as the power property. So notice what's going on here. Let me put this in like a different sort of silly symbols. So what we have is log base a of stuff to the power p, all right, is equal to p times the log base a of stuff. And I'm calling it stuff just to emphasize that it has to be all of the stuff raised to the p power. All right, like what can you do, what can't you do? Let's look at a couple of examples. So like example 1, if I have log base 3 of, 9 times 3 squared, all right, it is not equal to 2 times log base 3 of 9 times 3. Why? Because the power 2 does not apply to the entirety of what's in the exponent, in the logarithm, all right? Do you see it? In order to apply the power property for the log, I have to have everything raised to the power. So in order to make progress on my example 1, unless you got a calculator, right? If you got a calculator, you can always do these problems with a calculator. But the reason I don't have a calculator out is I'm trying to illustrate properties of logs without, picking up a calculator. So this is really what? This is equal to log base 3 of what? 3 is what? 3 squared. So this is actually 3 to the what?
9.
3 squared times 3 squared, which is what? The log of 3 to the power 4, which is what? That's 4, right? If I continued what I have up on the top, what would that be equal to?
22 log.
Yeah, this 27. 27 is 3 to the 3, right, Michael? So that would be 2 times 3, which would be 6.
Oh my gosh.
And is 6 equal to 4? Unfortunately not, right? Why did this happen? Because I misapplied the power property, right? You cannot pull the 2 out unless it's everything to the 2 power. All right? It has to be everything to the power to use the property, the power property. Yep.
So what would that one look like if everything was raised to the same power?
Something like this, say log base 7 of, I don't know, 7 squared x squared 81 times 81. So in order to use the power property, I have to have everything is raised to a power inside the log. So like for this silly example I just made up, I have to write 81 as a power, right?
9 squared.
9 squared. And I think I might have missed a, I'm trying to think if I missed a law of exponents over here. What is this I'm using? Once we have, if I have like a to the s times b to the s times c to the s, I can rewrite that as abc to the s power. I suppose that's a couple of the laws of exponents I wrote over there working in concert, but I just think of this as a rule of algebra that I know. All right, so if you don't know this already, this would be a good one to just kind of like memorize and have that on your list of things you can do in terms of algebraic simplifications, right? But in order to combine things into a like power, we do have to have the same power shared. But I have that now, right? 2, 2, 2. So this is log base 7 of 9 times 7 is 63. And I've got an x, all of that squared, you see? And then, now that I have the square on everything, I could pull the 2 out. So this would be 2 log base 7 of 63x. Are there any other things we could do to this expression? Like, what else could we do? Well, I'll just stop with that. Enough for this example, but these examples I'm currently doing, they're kind of meandering. This is, I haven't really stated a problem, right? We're not solving a problem, are we? What am I doing? I am merely illustrating how the laws of logarithms work for you on specific expressions, all right? In your homework, you'll have like a task to do. Let me show you one of those. Here's one. Collect all terms into single logarithm. All right, so you might be up against something like log of 100, oh my bad, log of x plus 2 log of y, minus 3. There, we'll start with that. So we want to collect these all into a single log. Yes, Michael?
That's what the problem I was stuck on. Problem number 85 with the minus 3.
85 is like that. 85, this is how, so you're stuck on problem 85 because of the minus 3?
Yes.
Ah, well, let me show you the secret of the minus 3. Now, first of all here, I need to confess there's some special notation, right? I used log base 7 for example 2. I used log base 3 for example 1. There are really 3 common log notations that you need to know about. Common log, that's kind of funny, because this is called the common log. So, so common log. Common log is just log, which is technically, in our usual notation, log base 10. The natural log is, we use ln for natural log, and that is technically log base e. All right? Did I say there were 3?
Yes.
It's really just these 2. I mean, there's other weirder things, like if you're a computer scientist, you might run up against the this thing LG, I think it is, which is like log base 2, but whatever. Pretty much for my course, if you know the log without anything is log base 10, and the ln is log base e. Those are the 2 ones you need to know about, okay? Now, if you were confused on the test and didn't know, you could ask me that, I'd tell you that. That's not a big deal. But, all right, so some of these things we can take care of already, right? These 2 we can combine using the properties. What we got? We got, well, one step at a time here. I've got log of x plus the log of y squared.
Sorry.
And then the 3. What is the 3? You got to use your imagination. Check this out. So minus the log of 10 to the 3. See, I can take any number and convert it into a logarithm. Check this out. If I wanted to convert 5 into a log base 7, here's how I do it. 5 is log base 7 of 7 to the 5. There you go. I just rewrote 5 as a log base 7 of a particular number. This game you can play. Yeah.
Would there be any incentive to pick specific log numbers to match a common term you're trying to turn into a log, or no?
Yes. In this case, we wanted to use the same log we're already up against, which is the common log. So that's why I did the 10. Now, you know, so for the common log, we have this identity, like log of 10 to the whatever is equal to the whatever. And likewise, 10 to the log of y, let's say, is equal to y. These are the identities which are true for the common log. For a natural log, instead of having the 10, you have an e. All right? We'll do some of those in a minute. But now that I have this, we can use the properties of log, right? We can do what? This is what? This is log of x times y squared, right? Minus the log of, well, 10 to the third power is 1,000, right? I'll just write it like that. And then which can I do? I want it, my instructions were collect all terms into a single log. So what's left?
So basically it's x times y squared divided by 1,000.
That's right. It's the log of x times y squared divided by 1,000. Now you might wonder how it is that Michael has an unfair advantage and he understands what I'm doing today. I will tell you, he has a secret. His secret is he's doing his homework. If you do your homework, you too can be like Michael and understand what I'm doing. Now some of you are relishing in the fact that you've had a Thanksgiving break and you're just going to put it off till then, right?
No,
No?
I will study.
You will study? Okay. So, when is our test? There's another test, isn't there? Is it before or after Thanksgiving break?
It's after.
After.
Say October. It's November 1st.
Yeah, it's like
Yeah.
9 days, months.
Yeah.
Test is the very next day.
Okay, so the test is the Wednesday after break, yeah. So, got a little time, but it would sure be nice to go into Thanksgiving break having finished the mission, right?
That would be nice.
That's where you'd like to be, right? All right. Any questions about this?
Oh,
Yeah?
So, on problem number A7, it says expand the expression and rewrite it in terms of A equals log X, B equals log Y, and C equals log Z. What does that mean?
Okay. So we're supposed to, given this, so this is example 4. Notation, you know, this is a given notation from the problem.
It's a natural law, looks like.
And then we were supposed to expand.
Yeah, expand the expression.
So expand, let's say, the log of, oh, I don't know. The cube root of x y squared divided by 10z, and write the answer in terms of just A, B, C, and appropriate numbers. In other words, use the property of logs to simplify this expression by expansion. So instead of collecting things together, we're going to break things apart this time. It's the opposite of example 3. So, and I think that you said problem 87, Michael?
Yes.
Probably 87 is easier than this, isn't it? Maybe a little bit. So let me start. I'm just writing down what I have up there again. So we've got the log of the cube root of xy squared divided by 10z. So let's start out by using the division property for the log, which says that this is really the log of the cube root of xy squared minus the log of 10z. You guys with me? I'm saying that the cube root is like the u in my formula over there, and the 10z is like the w in the formula on the far board. All right? Then what can I do? What is cube root? That is xy squared to the 1/3 power, right? And there I've got minus log of 10, I'll put some parentheses here, plus the log of z. So I went ahead and used the log of a product as the sum of the logs to split up my 10 and my z, all right? And I'm just reminding you that cube root is 1/3 power. But now we can use the what?
Now we can use the
What can we do with this third here? What can we do?
move it over.
Move it out front, right? That's the power property of the log. So this is equal to 1/3 log of xy squared, and then minus the log of 10 minus the log of z.
Minus.
What's log of 10?
The common log.
Okay, but what is log of, so we've got log of 10 is log base 10 of 10 to the 1. So what's it equal to? Something you should know going forward, guys, is if we ever have log base a of a, you just get 1.
Log A.
That's something to... So log base 10 of 10 is just 1. This is just 1. So the log of 10 is just 1. And the first one, I can use the power property log again. This is 1/3 parentheses log of x plus the log of y squared. All right. And then I've got minus 1 minus log of z. But what can we do with that log of y squared? We can do what? We can use the power property for the log again. We can take that 2 and pull it out. Pull it out. All right, so what's this give us? This gives us 1/3 log of x plus 2/3 log of y minus 1 minus the log of z. Now I have to follow the instructions of the example, right? Which was to what? Write your answer in terms of a, b, c, where a, b, c are given as log x, log y, log z. So what's the answer?
A equals 1/3.
Well, not a equals 1/3, but log x is a. So this is 1/3 a. Log y is b. So plus 2/3 b. Minus 1 minus c. And there you go.
This is the expanded expression. It's not just this one.
So I've expanded. What happened? Was that?
No, that just took like a lot of space on my page.
Oh.
Can you go through that purple step again?
I was imagining somebody, you like sent someone a text 7 years ago and they just now responded or something.
Oh.
But no, okay. What's that?
Never mind, I figured it out. I just had to look at it really closely.
Oh, okay, good, good. Yeah, now I can do this in like less steps, right? And so can you once you learn things. I am going slow and being quite expansive and emphasizing every last little step because we're starting this material today, right? At the end of this, once you're mature and know what you're doing, this goes much faster, all right? And certainly, if you're already mature and already understand this more deeply and don't want to write down 1, 2, 3, 4, 5, 6, 7 lines to do it, you can do this in 2 lines correctly. More power to you. Great. I'm just trying to emphasize every single property as I'm applying it at the moment. That's all. So, okay, enough of this. Let's go back to, well, there's a couple things we can go back to here. One is, why are these properties true, right? We could try to prove these properties. I don't feel inclined to do that today, so let's not do that. But some other day I'll come back and, you want me to prove them?
It's your choice.
Well, let us. Now, I should take some time to remind myself how it is that I want to prove them, because if I just try to prove it on the fly, what tends to happen is I find a really complicated way of proving them, and then like 20 minutes later, we're all like, why did you do that? So let me just spare you that. Once it comes back to me clearly how to prove them nicely for you guys, then I'll show you some other day. They are true. And they are just really, they really are nothing more than translating these rules into the log notation. All of the log properties are just the exponential properties rewritten in log notation. That's actually what's going on there. But saying that and giving you a convincing argument for why that's true are 2 different things. So what I'm going to do, since I know this is probably more useful to you in the long term, is talk more about how to solve equations, all right? So we have looked at solving equations last time with what? The one-to-one property. Let's start thinking about how to solve equations using logarithms, all right? So check this out. Example 5. Suppose you have 2 to the 3x plus 1 is equal to, 2 to the x squared. Did I say 3x plus 1? I meant 3x minus 2. There we go. I feel better about it now. So, listen, if you remember what we did last time, you know how to solve it. But I want to show you a new way of thinking about it. And my new way of thinking about it is this. We can take log base 2 of both sides. If I take log base 2 of both sides, what happens? Well, remember, log base 2 and the exponential base 2, these are inverse functions, right? So that gets us to 3x minus 2 equals to x squared, which of course is where you would have directly got to last time by the one-to-one property. Granted. And that's still how you should do it. I just want to point out you could think of it this way. Once you get here, then you know what to do. Put all your x's on one side. Obligatory Taylor Swift joke. Let's see here. X minus 1, x minus 2 equal to 0. And solutions are x equals 1 or x equals to 2, right? Hooray! But my point to you is we can manipulate the equation we're given from the exponential format, out of the exponential format into just the, let's say, standard equation format by simply taking the log of the equation, all right? And so maybe it'll be less surprising in my next example when I have, oh, I don't know, 2 to the 3x minus 1 is equal to, let's say, 7 to the x plus 3. How would I solve that?
Turn it into log 2 and log 7.
And turn it into log 2 and log 7. What was it, Michael? What was your?
Turn 7 into a factor of 2 to the power.
Turn 7 into a power of 2.
That sounds fun.
How would you do that? I like that a lot. That's actually a really good answer. But how is that achieved? How can you turn a power of 7 into a power of 2? Anybody know? Can you do that? Can you turn a power of 7 into a power of 2?
I don't think we know how to turn anything into a power of 2 yet.
I'm going to come back to that idea after this. That is something we can do, but let me do this the way that I usually do it. So you could either, like, there's two natural choices here. Log base 2 or log base 7, right? Either log base 2 or log base 7 at least gets rid of the ugliness on one side or the other. But the bad thing about both of those choices is if you look at your calculator, you're going to find out that log base 2 and log base 7 are not readily available. All right? But what is readily available is the natural log. There's a big old honkin' natural log button on all of your calculators. So I'm going to, just to be equally rude to 2 and 7 at the same time, I'm just going to use the natural log. I'm going to take the natural log of this equation. Natural log of 2 to the 3x minus 1 equals natural log of 7 to the x plus 3. Now, what can I do with that? What do I do? I've got what? I've got a logarithm of something to a power, right? Both sides. So I can pull it out. I can pull it out by the power property of the log. And when I do that, let's do that. 3x minus 1 times the natural log of 2 equals to x plus 3, parentheses are your friends, natural log of 7. Now natural log of 2 and natural log of 7, those are numbers. Your calculator can tell you approximately what they're equal to. There it is. How do you solve for x? So you're like 3x log 2 minus x log 7 is equal to the log of 2 plus 3 times the log of 7. So it's just take all your x's and put them on one side, and take all the things without x's and put them on the other side. All right? Then factor x out. So we've got x times 3 log 2 minus log 7 is equal to log 2 plus 3 log 7, which gives us x is equal to the log of 2 plus 3 times the log of 7 divided by 3 times the log of 2 minus the log of 7. And there you go. That's the solution. So with the natural log, we're able to solve problems where we have different bases on one side and the other. All right? Example 7, I'm going to do what Michael said. I'm going to take that 7 and I'm going to convert it to a 2. How would I do that? 7 to the x plus 3. How do I convert that to a power of 2? We have an identity. 2 to the log of anything is the anything. So I will just do that. This is equal to 2 to the log base 2 of 7 to the x plus 3. Which is, by the way, equal to 2 to the x plus 3 times the log base 2 of 7. So another way to do example 6 is this. But I think this is kind of a weird way to do it, isn't it? So we'd have 2 to the x, 3x minus 1 is equal to 2 times x, 2 to the x plus 3 times the log base 2 of 7. And then we can go back to last class, and we could use the one-to-one property. Yeah? We could solve it with the one-to-one property. And that would give us 3x minus 1 is equal to x plus 3 times the log base 2 of 7. All right. And we could finish from there, but I want to spend the rest of the time on the quiz, so I'm just going to leave that there. All right.
Oh my.
So, listen, we're not done by any stretch of the imagination. Like, we've got lots more examples of these to do. But this is a good start.
Well, I'll do them to the best of my ability.
That's all you can do, right?
Yeah.
Now, annoyingly, last time I gave this quiz, it ended up being number 10. It is currently number 8 for you guys, so don't pay too much attention to the number here. Let me find my laser.
Not a fiery inferno this time?
No, I threw out those batteries. I think it was the batteries that were messed up. All right, so what was problem 1? Problem 1 was we were considering the what function here? Consider x squared plus 3 is a one-to-one function. So if we do algebraically, we set f of a equal to f of b, and we get a is equal to plus or minus b, so no, it's not one-to-one. Of course, graphically, you're looking at a quadratic, so it fails the horizontal line test, right? So not a one-to-one function. Now problem 2, I said to find the formula for the inverse function, and I hope some of you were able to successfully do this. If not, keep working on it. So what we do is we write the formula y equals f of x, and then my goal is simply to solve for x. So I multiply to the other side, and I multiply it out. I put all my x's on one side and everything without x on the other. I factor the x out, and then I divide and solve for x, and there you go. That's the inverse function as a formula in terms of y. And if you write it in terms of x, that's the formula. All right? How many people feel like they got it this time? It's about a third of you right now, yeah? But you're getting there, right? You see you can't, yep.
I got to.
Oh, you're asking, is this a legit answer? Yeah, that's a legit answer. I don't like minuses. I try to keep it positive, you know?
So keep them all positive?
Well, oh, did I ask about range?
Yeah.
Oh, yeah, so the domain of f inverse, of course, is everything except for minus 3, and that's the range of the function. And the domain of the function is, you know, everything except for minus 2, because there was a division by x plus 2 in the formula. Now, Michael, don't worry. I'm going to post this in Canvas so you can look at it there, okay? Don't sweat it. Problem 3. Problem 3 we probably could have done last class, because we would have converted the 4 to a 2 to the 2, and then we'd have 2 to the x squared equals 2 to the 6x, which then by the one-to-one property gives us x squared equal to 6x, which we can factor an x out, and we get either 0 or 6. Hooray. Problem 4, on the other hand, that is definitely outside our scope last class. But now that we know what is a logarithm, we can take the natural log of both sides, power property, pull the x out, power property, pull the 3x out plus 1, and then put all the x's on one side, put everything without x on the other side, factor the x out. I keep saying the same set of steps, don't I? Yeah, the algebra in this and the algebra in finding the inverse function, it's the same algebra, isn't it? So we've got natural log of 7 over natural log of 2 minus 3 log 7. And I usually, when I have a problem like this, I have some instructions like please leave your answer and like give a decimal approximation for your answer, like up to a certain number of digits, because otherwise there are many other ways to write the answer in terms of logs which look nothing like this. It's really annoying from a grading perspective. And then finally, it looked like that. See, take the point, flip it. Take that point, flip it. Take that point, flip it. Connect the dots, inverse function. You can double check the domain of the function which is given, minus 8 to 6. The range of the function that's inverted, minus 8 to 6. The range of the function, minus 6 to 8. The domain of the function, minus 6 to 8. We have the proper flippity-floppeting of the domain and range. That's a good sign that my picture is probably on the level. Anyway, thanks guys. See you later.